Hello and welcome to Honors Function. In this video, we're going to be focusing on an important property of a function, the interval of increase and decrease, where the function goes up or down, and the corresponding concept of a maximum and a minimum for a function, either global or local. Let's begin. So suppose we have the graph of a function like this one, and we will be dealing with this kind of graph in the next unit. We want to say where the function goes down, like here for example it goes down, and here it goes down, and where it goes up, and for example we can see that it goes up here and there, okay? But seeing where the function goes down and goes up, that's not precise. We need something much more precise to describe it. So what do? Well, let's go to the next graph. Okay, so on this graph, the function constantly goes up. This constantly going up is called monotonous. Okay, in mathematics, when you don't change the going up or going down, you say that the function is monotonously increasing. This function is monotonously increasing. Check out the word, it's in my notes. So how do we describe it algebraically? Let's look at two inputs. Let's say this one, x1, and let's take an x2 right here, okay? So the order in the input is that x1 is smaller than x2. That's the order. Let's check out the order of the output. So where's f of x1? It's right here. And where's f of x2? It's right here. And what do we see? We see that the order in the output is the same as the order in the input. Same as f of x1 smaller than f of x2. And this is actually the characteristic of an increasing function. We say that an increasing function preserves the order, okay? The order of the input is preserved in the output. Let's look at the graph of a decreasing function. So if you see this graph, this is a graph of a function that is also monotonous, but this time it's monotonously decreasing, okay? Here, I hope you found the word in my note, monotonously decreasing, okay? Decreasing. Monotonous function. Monotonous right here. All right. Let's look at the order again. Check out the order. I'm going to take an x1 right here, and I'm going to take an x2 right here. So here again, I have that x1 is smaller than x2. Let's look at the order of the output. So f of x1 is right here, and f of x2 is right there. And in this case, you see that the order is no longer preserved, but you have a reverse order in output. Right? Output, you have f of x1 is greater than f of x2. We say that a decreasing function reverses the order. And that will be the characteristic of decreasing and increasing. This is how you're going to measure decreasing and increasing, by looking at the order. Is it preserved or is it reversed? And of course, if we go back to the first graph, here it depends on the interval. The function sometimes will be increasing and sometimes will be decreasing. For example, right here the function is decreasing, and then it stops being decreasing right here and it increases, right? So you see this point plays a capital role. Okay, the function from here to there, I'm describing the x interval right here, the function is going to be decreasing right here, right? Decreasing, but then it's going to be increasing, I guess, until the y-axis right here, and then from here to there, it is increasing, then decreasing again right here. Do you see that? It's decreasing, and then it's increasing again. So it can change its increase or decrease, and then these points are going to play a very important role to describe where the function is increasing or decreasing, okay? All right, I'm going to let you check out the definition of increasing and decreasing, and I want to go over the first example. All right, here we go. First example. This is a graph of a function. I want to know the range, so that's pretty straightforward. The range is from a negative infinity to what? To 7.5 0.39. Please do not describe the x. Oops, mistake right here. It's a bracket. Okay. Interval of increase. Well, check it out. My function is increasing right here. It's increasing up to this point, right? The interval of increase has to be an x interval. The function is increasing from negative infinity until this point right here, okay? So from negative infinity until negative 2.22. Here, it doesn't matter if you put a parenthesis or a bracket. At a point, at a given point, the function is really neither increasing nor decreasing. Well, let's put a parenthesis right now, actually. I'm saying something that is not completely precise there, but let's just put a parenthesis, but it doesn't matter, okay? Then there is another interval of increase that is between here and there, right? I see my function is increasing between these two x coordinates, so or union, so it's 0.21, and then where am I? I'm at 2.38, 2.38. That's it. These are my intervals of increase. What are the intervals of decrease? I'm going to do something a little bit radical here. I'm going to hide my graph. Check it out. Oh, what am I doing? What am I doing? What's going on here? I don't need the graph to describe the interval of decrease. I just need this. And also I need to know that the function is never constant, okay? It's never a straight line. If it's not increasing, it is decreasing. So my first interval of decrease will be between these two values. So I have negative 2.22, 0.21, and what's the next one? Well, it's not going to be decreasing here, right? So you got to go after that. So it's going to be 2.38 and then forever, because it's never increasing again, so it's going to be always decreasing, okay? And these are going to be my interval of decrease. I hope it's clear that you do not need to look at the graph. Check it out, okay? But you don't need to look at the graph to answer this question. All right. The zeros. Well, the zeros are right here. Let me erase all these mark here, okay? It's getting a bit confusing. Here we go. So I have 1, 2, 3, 4 zeros. You're gonna have to check out the scale, right, to read the zeros. So this is 5, 4, 3, 2, 1. Okay, right. So I have negative 1 is a 0. I have 2, 3, negative 3 is a 0. Then I have, what is this? I'm guessing this is 1.5, right? 1.5 is 0. It's not clear enough, but anyway. 2, 3, and 3 is a 0. The x-intercept, well, hey, if you get the 0, that's pretty straightforward. Negative 1, 0. Negative 3, 0, 1.5, 0, and 3, 0 are your x-intercept. Y-intercept, I'm giving it to you. It's right here. It is going to be 0, negative 5.4. Here we go. That's it. Okay? Let's go over a second example. I'm going to let you do number 2, and I'm going to do number 3. Number 3. Find the interval of decrease of this function. Well, we know this function. We know it's a parabola. So we know it's either going to be like this or like this, right? And therefore, I'm going to need the vertex and actually just the x-coordinate of the vertex, right? So let's go fetch it. Here, let me divide right away by 1.2. So I have x squared minus 36 by 12 is 3. So minus 3x. And then minus, and I really don't care the rest right here. Check it out. Why? Because I got my the x-coordinate of the vertex. X minus 1.5 squared minus blah, blah, blah. And that's it. That's enough. This is the x-coordinate of my vertex. It's 1.5. It's 1.5, right? So 1, 2, my axis of symmetry is x equals 1.5 right here. X equals 1.5. My function is concave up. My function is like that. And so the interval of what do I want? I want increase first. Okay, the interval of increase is going to be from 1.5 to infinity, and then the interval of decrease will be from negative infinity to 1.5. That's it. Okay, we know everything there is to know about a parabola. All right, I'm going to do 4 and 5 because these are a little bit tricky. Let me tell you first of all what that says right here. What are we looking at? We're looking at the function f of x equals 1 over x, and it's a function you should have seen in algebra 2. The function goes like this. See, the function goes like this, right there. It's called a hyperbola, okay? And then it goes like this, right here. Now, I'm looking at it only on the positive side, so I'm looking at this branch of the hyperbola. And the function is going down, right? The function is going down. So the function is decreasing. The function is decreasing. Now, we see that graphically, but that's not the proof. I'm asking you to prove that it is decreasing. I'm asking you to prove that the function is decreasing, okay? So the proof is not difficult. Check it out. I'm going to do it because it's a proof, okay? And it's never too fun. So look, you have 0, actually strictly smaller than x. I cannot divide by 0. 0 smaller than x1, smaller than or equal to x2, right? Let's multiply both sides of this inequality by, I'm looking at here. When I say both sides, I'm looking at this, okay? Let's multiply both sides by 1 over x1. Can I do that? Am I allowed to do that? You can multiply both sides of an inequality by a number, right? 1 over x1 is positive. Therefore, I am not going to switch my inequality. Okay, 1 over x1 is positive because x1 is positive. All right, so I'm not going to switch my inequality. I'm allowed to do that. What do I have? I have that 1 is smaller than x2 over x1. And now what? Well, now I'm going to multiply both sides by 1 over x2. Again, I don't need to switch my inequality. It's all positive. And so what do I have finally? I have that 1 over x2 is smaller than 1 over x1. Therefore, what do we have? We have a reverse of inequality. Reverse, right? x1 was smaller than x2. But 1 over x1 is larger than 1 over x2, right? So the function y equals 1 over x is decreasing. We proved it. That's a proof, okay? I will use this pretty commonly in my inequality. Whenever I deal with inequality and I take the reciprocal, I will flip it like that, okay? Let's do the next one. Actually, be careful, guys. I've made a mistake in my notes. Of course, here, let me show you. You know the square root graph, right? You should have seen it again in Algebra 2. The square root graph goes like that, and therefore the square root graph is an increasing function, and therefore it preserves the inequality. Okay, I've made a mistake right here. It should be like this. Now, this is a little bit more challenging to prove this one. Okay, so I'm taking two real numbers, x1 smaller than or equal to x2. Here we go, right here. All right, now, a real number is always, it's positive right here, okay? Sorry, I didn't say that. A real number, a positive real number is always a squared of another number. So x1 is going to be the square of a number that I'm going to call alpha 1, okay? x1 will be the square of alpha 1 squared, okay? A real number always has a square root. Actually, it has two square roots, but one of them is positive, okay? And that's a square root right here. And x2 is going to be the square of another real number, okay? Because they are both positive, both square roots, alpha 1 and alpha 2, will exist, all right? Now, what does it mean that x1 is smaller than x2? That means that, okay, here, I'll do this symbol right here. That means that 0 is smaller than x2 minus x1, okay, which means that 0 is smaller than, so x2 is alpha 2 squared. Alpha 2 squared minus alpha 1 squared, right? Which means that 0 is smaller than, let's factor this, alpha 2 plus alpha 1 times alpha 2 minus alpha 1. Now, let's pay attention to this right here, okay? Alpha 1 is the square root of x1, which means the positive root of the equation, you know, blah, 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 equals x1 squared, right? So, the square root exists. Alpha 1 is a square root of x1 and alpha 2 is a square root of x2. Okay? Now, a square root by definition is strictly above 0 by definition of the symbol right here, okay? So, alpha 1 plus alpha 2 plus alpha 1 is going to be strictly above 0. If they're both positive, you're not going to find something negative when you add. So, this is positive, okay? It's not 0 because none of them are 0. Therefore, right here, what I can do is divide both sides by alpha 2 plus alpha 1, right here. Okay, I'm going to divide both sides by alpha 2 plus alpha 1. What do you have? This cancel. I'm going to go right here. On the, sorry, it's a bit like all over the place. what do you have on the left? 0 divided by alpha 2 plus alpha 1. Well, that is still 0, smaller than alpha 2 minus alpha 1, and then add alpha 1 on both sides, and you have that alpha 1 is smaller than or equal to alpha 2. Therefore, square root of x1 is smaller than or equal to square root of x2. Okay, we proved that the function y equals square root of x is decreasing. All right, now I'm not going to ask you to prove something like that in any of my quiz or tests. This is a little bit challenging, but please look at it one more time. Please look at it one more time. You have to assume the existence of a root right here. You have to assume that the root exists, and after that it's all about factoring a difference of squares. That's it. That's all. Okay? All right. Let's go over the concept of maximum and minimum now. For this, I'm going to be using the graph that is in my notes right here. Here's a graph of a function. And let's look at the points I've talked about earlier. This point right here, this point right here. So this is a trough. Okay, this is a trough. Some people call it a valley. It's a mean, but the graph is described as a trough. This is a crest. Crest and trough. Another trough right here. Trough. And another crest right there. It's a tiny crest, this one, right? Anyway, there's a crest right there, all right? Troughs and crests, okay? So a trough describes a minimum value of the function. At the trough, you're going to have the minimum value of the function, right? And at the crest, you're going to have a maximum value of the function. So this one right here, there's nothing lower. Look, this y value, there's nothing lower than this y value, right? Any line right here will not touch the graph, right? This is the lowest line possible. So this y value right here is called an absolute mean. Absolute mean. Be careful, it is not the point that is called an absolute mean. An absolute mean of the function is a y value. What is the x? It's where the absolute mean is, okay? So this is the what is the absolute mean. What is the absolute mean? What is? And this is the where is the absolute mean, okay? The x gives you the where, and the y gives you the what. This is an absolute mean. Let's check out the other trough. There is another trough right here. Right here, you got a trough right there, right? So what's going on here? This is a mean too, right? But here, let me zoom in right here, like that. It goes like this, right? So here's the y-axis. So around this value right here, you got a mean right there, right? But this is a local mean. Why? Because, and this is the x-axis, because around it you don't have anything lower. There's nothing lower around it. But of course, if you go a little bit further, like this one right here, this y value is smaller than this one, right? So this is not an absolute mean. There is always something lower in the graph. This is a local mean. And again, you're going to have the what on the y-axis. What is the local mean? It's going to be the y value. And where is the local mean? It's going to be the x value, okay? And what I just said for a mean is also true for a max. This is an absolute max, and this is a relative max. Actually, I wrote relative right here, but I prefer the word local instead of relative, okay? And I prefer the word global. This was my old terminology. I like the word local and global because I can say them better instead of relative. Anyway, local and global, please, okay? Let's go on with the next example, which is going to be a calculator one. I want to show you how the calculator can help you compute or find these local mean and local max. Let's go. So suppose you want to figure out the local mean and or absolute mean of this function, if it has any, okay? A function doesn't have to have anything, we'll see that. How do you do it with your calculator? Well, first of all, you need to plug the function in your calculator. So let me take my calculator. Okay, let's plug in the function. Negative 0.2 x cubed plus x squared plus x squared plus x minus 5 plus x minus 5. Now the first window I'm looking at always is a zoom standard, and if that's not enough, then I'll do something else. Zoom 6, zoom standard. And that's a fine graph. That's a fine graph. So I see that the function will not have any absolute, global. The function will not have any global max and global mean. Okay. So let me just grab this one. I'll let you grab the other one. There, it's a similar way. Okay. You gotta go in the calc menu. Calc is second trace. Second trace. Calc menu. And you see you have a couple of options right here. I want the mean. So that's number 3, mean right here. And now my calculator is asking me left bound. So you have to bring the cursor on the left side of the mean. So I'm not on the left side, and right here I'm on the left side. All right. Yep, that's going to be my left bound. Enter. Then right bound. So you go on the right side right here. Just make sure you just passed it. And I'm pretty sure I passed it right here. So I'm going to push enter. That's it. Guess. I'll tell you in class what that means, but you don't need to guess. Just push enter. And here we go. You have the where is the local mean, and the where is negative 0.44, and the what is the local mean, and the what is negative 5.22 right here. Okay, the y is the what, the where is the x. All right, I'm gonna let you do example number 6, and I will finish with one more example of a problem. So let me go back to my notes and do example number 8. So here we go. Example number 8, what do we have? We have a parabola, and we have a point outside. I'm assuming it's outside the parabola. Let's quickly check what the parabola is. So negative y equals x squared minus 6x plus 3. I multiply by negative 1, right? So it's x minus 3 squared minus 9 plus 3 is minus 6. So we have y equals negative x minus 3 squared plus, I multiply by negative 1, right? This is a minus y. I multiply everything by negative 1 plus 6. Let's quickly check this, sketch this graph. So vertex, I'm not going to do anything too precise, okay? Vertex 3, 6, so 1, 2, 3, 1, 2, 3, 4, 5, 6. Here's my vertex right here. And then my graph is just going to go down. So it's going to be something like this, like that, and like this. Where's the point 2, negative 5? 2, negative 5 is going to be somewhere here, okay? And I will want the shortest distance, so I'm not sure exactly. So what you do right here, you take a point on the graph right here, for example. I don't know if this is going to be the shortest distance. You remember that's what we call usually d of x, and x is the coordinate of this point. We've seen that before, right? This is the point x, y, right? And this is the point 2, negative 5. So what is, and I want d of x, I want the function this time as a function of x. What's the distance between 2, negative 5 and xy? It is square root of x minus 2 squared plus y plus 5 squared. Got it. Now, I want to make it a function of one variable, not two, so it kind of makes sense to use this. This is your y, right? So it is equal to x minus 2 squared plus, and here we have what is y? Y is negative x squared plus 6x minus 3, minus 3. That's my y right here. And then I will have the plus 5 squared right here. Okay, this is your y, right? And so what do we have? We have that the function d of x is actually, so d of x is square root of x minus 2 squared. Don't bother expanding this, plus what? Plus negative x squared plus 6x plus 2. That's it, okay? You could expand it if you want to, but it's going to be too cumbersome. I'm not going to expand it. This is my function, and I want to know what? I want to know where it's going to be minimum. Maybe on this side, I don't know. I didn't do a precise graph, right? Maybe on this side, but what is it going to give me? It's going to give me the x value right here. It's going to give me, I'm going to find an x value of the point where this distance is going to be minimum. How do I do that? Well, we need to graph it. I'm telling you to use a calculator on this one, okay? So let's go back to the calculator right here. Let me go to my y, Let me clear this one. Okay, let's enter the function. So we have square root of, so x minus 2 squared plus parenthesis. So we have negative x squared plus 6x plus 2, close the parenthesis, square this, and I think that's it. Let's get out of the root, and that should be it. So let me go to a zoom standard, zoom 6, and let me see what we have. All right, okay. I see a minimum somewhere around this point right here. I don't like this window too much. It's not that clear, so I'm gonna cut it off. I'm gonna cut off all these x min right here, and okay, let's see. So window x min, I don't need anything smaller than, let's say, negative 3. X max, I don't need anything greater than 8. Y mean, surely it's all a distance, so I don't need anything smaller than negative 1, and I'll keep the 10. Let's see if this graph is a little bit better. Yes, that is much better. Here we go. All right. And so I see that the minimum distance is going to be for an x right here. Okay, so let me grab it, and I have calc right here, minimum 3, and where's my cursor? Left bound. Where's my cursor? I don't see my, oh, it's coming down right here. So left bound right here, left bound right here, enter. Right bound right there. And the question is, careful, the question is, use your calculator to find the minimum distance. So the minimum distance is going to be 2.29. Okay, you want the y, that's my distance. On the y-axis you have the distance. You graph the function d of x, right? So the minimum distance is going to be 2.3 units. Okay, 2.3 units. So the minimum distance is d of x is going to be about 2.3 unit. That's a minimum distance. Okay, minimum. All right, that's it. This video is a little bit long. I'm sorry about that, but it's a very important concept. Thank you for watching.